Part 2. So I shared with you many of the most important fun facts about eigenvectors last time. I will just give you a brief recap. Definition, right? We say that if you have t, a linear transformation from V to V, then x not equal to 0, such that t of x equals to lambda x is an eigenvector with eigenvalue lambda. And we're assuming here that this guy is a real number, for the moment at least. All right, now, of course, we immediately then said, well, that's nice, but wouldn't it be nicer to instead look at this and really saying that t minus lambda times the identity acting on x is equal to 0, right? Which then says that the kernel of t minus lambda times the identity is not equal to the set containing 0. All right. And because of that, it must be that the determinant of t minus lambda times the identity has to be equal to 0, because this linear operator t minus lambda times the identity is a linear operator such that it has a non-trivial kernel, right? And that means that it's not invertible because it can't be injective. So we need to make a couple definitions. And these definitions are, of course, born on the more careful discussion of last time. But here they are. Definition. First of all, and okay, so, and by the way, obviously we also basically we're gonna say, okay, well, we know that t can if I say t of v in the beta coordinate system, right? That's equal to t beta beta acting on d beta, right? And the kernel is connected to the null space of this matrix. And the determinant is defined in terms of the matrix. So pretty much we will just call this thing A, and we focus our attention on an n by n matrix and what follows. Okay, so I'm going to shift gears back to that again, talk about a matrix. All right, so first of all, given A an n by n matrix, we define a couple things. Well, p of lambda, all right, that's equal to the determinant of A minus lambda times the identity. Okay, this has a name. This is the characteristic polynomial. Characteristic polynomial of A. And so, characteristic polynomial of A. And so basically we can we have a little basically proposition that we already proved last time, but here's the proposition. Lambda is eigenvalue of A if and only if the determinant of A minus lambda I is equal to 0. In other words, if I wanted to just recast that in a simple sentence, I would tell you this. The eigenvalues are precisely the real roots of the characteristic polynomial. The eigenvalues of A are, or if you like, the real zeros of P of lambda, which is, of course, well, I'm just going to say that. We define P of lambda back over here. Okay. Now, of course, you can also talk about the characteristic polynomial of t, right? What would the characteristic polynomial of t be? Almost the same thing, right? You just replace A with T, right, and lambda. Instead of the identity matrix, I would use the identity. I've been writing id for an identity operator just to make a distinction between the linear transformation and the matrix. I is a matrix. Id is a linear transformation from B to B. Right? You understand the difference between a linear transformation and a matrix, right? A matrix is a box of numbers. A linear transformation is a function from one thing to another, right? These are rather different.
But they're linked together because of the proposition we have
Indeed.
between the B, R, and
Right. For the first part of the course, the fundamental theorem of linear algebra says that there always, anytime you have a linear transformation, you can always write it as a matrix multiplication and vice versa. And in the second part of the course, if you sort through the coordinate mappings, we also can always find a matrix which represents linear transformation. Fine print in the second part of the course, of course, is that that matrix is not unique, right? However, in the case that we're thinking about a linear transformation from a vector space to itself, where we're using the same basis in the range and the codomain, excuse me, in the domain and codomain, you know, when we change basis, we're just doing a similarity transformation, right? So if I chose a different T beta beta, it would just be like related to, say, T beta bar, it would be like P inverse T beta beta P. It's a similarity transformation between different choices. So yeah, in short, you're right. I mean, we can kind of, there's a correspondence, but nevertheless, be careful. One is a function, one is a matrix, right? So, all right, so characteristic polynomial, we need to know what that is. Of course, we need to know what eigenvalues of A are, right? But there's another important definition that I must share with you right now, and that is what's called the Eigen Space, the lambda of Eigen Space. So the Eigen Space. Now, in my notes, I use a W lambda. I'll use the notation of, just to get the notes, guys. What's this? Dimano? I don't know, it's like piano, like with a D. Dimano? No, Dimano.
Piano.
What?
Piano.
There we go, that one. And, oh, this one's safe enough, little. So they use this notation, E lambda. Okay, is the eigenspace associated with eigenvalue lambda for a given, let's say, matrix? It's really just this. It's the kernel of, well, okay, fine. It's the kernel of lambda times identity if we're working with linear transformations, or in the more concrete case, we use E lambda as what? The null space of A minus lambda I. So I would make one observation immediately. What's the smallest dimension that E lambda can have? So greater than or equal to what?
1.
1, right? Why is that?
Because it's a non-zero value for the kernel, so there has to be at least one thing that makes it 0.
Exactly.
That
So
isn't 0, and so on.
Precisely. The definition of eigenvector is that there is a non-zero vector, which is in the kernel, essentially. And so that's at least one thing in there. So the smallest the dimension can be here is 1. Okay? Now, I guess I need to make another definition. I really wanted to start doing examples, but I feel led to make this definition right now, so I'm going to get it out of my system.
And then go to examples.
Yeah. So if, you know, the determinant of A minus lambda I, right, is equal to, let's say, you know, let's see here, has 0 lambda with multiplicity. And I tell you what, I'm going to instead of using lambda here just to make it less ambiguous for those of you who don't like to think this way, let's put a T here just for the sake of, you know, being different. Okay, so here I'm looking at the characteristic polynomial using T as a variable, okay, P of T. So suppose that the characteristic polynomial has 0 lambda with multiplicity M, right? What that means is then, you know, what that means is that P of T is equal to something like T minus lambda, right? To the mth power times some other some other polynomial, let's say g of t. And what? What about g of t? What can we say? G of lambda is not equal to what? Yeah, not equal to 0, right? So to say that and to be more clear, there's actually going to be two kinds of multiplicity here, right? So multiplicity isn't going to make it for us. Multiplicity, well, I mean, that's fine. This is the usual use of the word multiplicity, right? I want to define what this, I'm making a definition. What have I defined here? We say then, lambda has what's called algebraic multiplicity. Algebraic multiplicity m. All right. I don't want to argue, I don't want to prove it right now, but a theorem that we can prove a little bit later, hopefully today, where we're going, okay, is to prove this theorem is that 1 is less than or equal to the dimension of the eigenspace, E lambda, which is less than or equal to m. In other words, the algebraic multiplicity is the top dimension possible for the eigenspace. That's the highest dimension that the eigenspace lambda can attain. At most 1 for each time you have a copy of the 0 appearing in the solution set characteristic polynomial. Yeah.
What is g of lambda?
Just some whatever's left. It's just a polynomial. You could say that, another way to say this would be that t minus lambda to the n, t minus lambda to the nth power divides p of t, but t minus lambda to the m plus 1 does not divide p of t. That's another language you could use to express the same if you wanted to think about polynomials dividing other polynomials. Okay, now, so those are the definitions that I need for our discussion today. But with that, I'm going to go and give you some examples. Okay, so if you don't mind, I'm going to erase most of this. I guess I could do the example. Let me do the examples over there. That way I don't need to erase all that. Be smarter, probably. I'm not going to pretend to be too smart. You get the wrong idea about me. So we can learn a lot from 2x2 examples. So let's do those. So example. How about a equals to 1, 1, 1, 1. That's a good one. So, what's the algorithm for solving these problems? Our goal here is to find the eigenvalues and the basis, and write each eigenspace in terms of the span of some basis. All right.
Just kicking the wall.
Yeah, sometimes.
I wasn't trying to make fun of you. I was just.
You can if you want. Okay. So I need to write our strategy over here. What's our strategy?
Find bases.
Yeah. So one, we're given A and asked to find eigenvalues and basis for each lambda, then the first thing we do is we calculate a characteristic polynomial, all right? And then the third thing we do is we start finding the eigenvectors, right? That's the order of operations here. So here I'm given the A, I know what I want to do. So first thing I do is calculate p of lambda. So p of lambda here is the determinant of A minus lambda I, right? Which would be what? It's 1 minus lambda. 1, 1, 1 minus lambda. See, because lambda I is what? What is lambda I anyway?
Lambda times A density.
Right. Yeah, so like A minus lambda I is actually what? It's 1, 1, 1, 1 minus lambda times 1, 0, 0, 1. Now I write that down about one time a year. Going forward, you know what's going to happen. You just subtract lambda from the diagonal entries, okay? We're good? Now you got to know those determinants we talked about before, right? So this is probably the most important application of determinants as far as this course goes. So this is, here's a fun fact. That's the same as lambda minus 1 squared, right? Think about it. Right, because minus a squared is a squared. I mean, I like lambda minus 1 rather than 1 minus lambda if I can have it. That's just how I roll. And hey, that's the difference of perfect squares. So that's lambda times lambda minus 2. Because you either add 1 or subtract 1. Of course, you can FOIL it out and cancel stuff and you'll get to the same thing. However you do the algebra, that's your business. Just do it right. Okay. Lambda 1, 0. Lambda 2 is 2. All right. So there's my eigenvalues. So let's look at 0. So we're trying to find, we wish to solve basically a minus 0 times the identity acting on, let's say, u1 equals to 0. We're trying to find a u1 that solves that, right? So, of course, 0 times the identity is kind of like, yeah, whatever. So what you really got is 1, 1, 1, 1 times some vector. I usually use u and v for a two-dimensional example. That's my go-to notation. All right. It's disposable. I don't keep, once I've done with this calculation, I kind of. So that's equal to 0, 0. Now, I don't think you need row reduction or anything here, right? This is clearly what? The same as what? This is the same as u plus v equals to 0. So without loss of generality, I have v is equal to minus u. And if you want to choose, you can pick anything you like. I usually pick u equals to 1 in this sort of problem. And then that tells me that E1 is going to be the span of, let's see here, 1 minus 1. So there you go. There's the Eigen Space E1 written as a span of an eigenbasis, which is the second any one vector, here than 1 minus 1. Yeah,
Isn't the determinant of a 2 by 2 AD minus BC?
Yep.
Then wouldn't it be 1 minus lambda times 1 minus lambda instead of lambda minus 1 times lambda minus 1?
I agree with everything you said except for the instead.
Okay.
Because 1 minus lambda times 1 minus lambda is lambda minus 1 times lambda minus 1. Because there's a minus, like the minus distribution. So basically just factor out a minus here, factor out a minus here, then minus minus is plus, which gets you to here.
Okay.
I don't know, that's just a trick I usually, you'll see this in my calculations, I always do this. Because, I mean, be careful not to do it for 3 things. We need a pair, so I mean. Yes, so how about the 2 eigenspace? What we got there? I think I'm going to work. I don't really think I need. Work myself into a corner. Okay, now I want to write here, but I want to keep this. Oh well. But I can't. It's fine. I shouldn't get sick is what it is. All right, lambda equals to 2. I should drink more coffee. I don't know. So now we're trying to find non-trivial solutions to a minus 2I, let's say times u2 equal to 0, right? That's the equation we're trying to solve. So that really just means to solve, let's see here. So subtract 2 from the diagonal. That gives me minus 1, 1, 1 minus 1, uv equals to 0, 0.
Do you do it from the diagonal because of the identity?
Yeah.
That's,
Oh, right. I mean, that's the very definition, is we subtract lambda times the identity, so, yeah. And that just means to subtract from the diagonal. It's always the same diagonal. When we have a 3 by 3, there'll be 3 lambdas.
Why bother with the D in the annotation over there? Like, since it's already going to be diagonal? Or is there something I'm missing?
Why bother with the what?
The D, like, yeah, or like, for example, like over in the definition over there, you say curve T minus lambda ID when I is already a diagonal.
Well, no, this notation is, this is the linear transformation from B to B, such that, it's okay.
Notation just kill me again.
It actually, you're still alive. And I mean, If I want to be more pedantic about it, sometimes I would use if V for that. That's the identity on the space V. If I want to be more, just like in the, to be honest, like even for the identity matrix, sometimes I'm more pedantic there, right? I would write an n, a little sub n there, indicate it's an n by n identity matrix. I mean, there's all kinds of shorthands going on here. Anyway, if you did it right, what should happen is we should have infinitely many solutions, right? So for two equations and two unknowns, that must indicate that your two equations are the same equation, which was stupidly obvious here, and is a multiplication by -1 obvious here, right? They're the same stupid equation. Pick either one of them without loss of generality, captures the solution set, right? So, I don't know, I'll pick the, which one do you want, first one or second one?
B.
What?
Second.
Second one. Okay, so that would be u minus v equals to 0. So that tells me that v is equal to u. So just pick, I can pick u equal to 1 if I like, right?
And then just do one.
And so then E2 is E2 is the span of 1, 1. There you go. There's the second eigenspace written as the span of, yeah.
What are you doing when you pick a value for u and v?
Making a choice.
Well, yeah, but like, what is it doing?
Because it's a span, it means that if you multiply any constant by it, it's like, it's an element of.
I choose 1 because it's convenient, right? Now, there is, you could argue, well, you chose poorly, but you should have done, you know, what your Texas Instruments calculator that you've spent money for would do for you, would give you some sort of ugly numerical monstrosity. But what it basically boils down to is 1 over root 2, 1 minus 1. And then you could also write this as the span of, and there are good geometric reasons for doing this, I'll tell you what in just a second. You know, you could put in any kind of scale factor. In particular, if I was going to pick a scale factor, I'd pick that one. Because if I pick that scale factor, then I have the, if I call this thing V1, if I call this thing V2, I would then have these nice things like the length of V1 is equal to 1, and the length of V2
I see.
is equal to 1. So they make them unit vectors. So if you wanted to make a systematic choice, you could always insist, I want to pick unit vectors, right? Or maybe you like the number 42. I don't know, you could always pick vectors with length 42 to form your basis. It's up to you.
So the u and v are just numbers you multiply whatever's in the standby to reach some object.
The one underlying rule that we must take care to be careful not to violate is we need non-zero vectors. So anything with 0 will work. But there's infinitely many solutions, so how do you want to write the solution? There's an ambiguity here, there's a choice. Now, once I make this choice, though, of scaling them to length 1, that makes the basis actually very interesting. This basis, if I use V1 and V2 as a basis, let's say, beta equals to V1, V2, since you asked me about this, Chris, suppose I construct that basis. That's a very special basis because each vector in that basis has length 1, as I'll talk about systematically Friday. But it's more than that. What's the dot product between these vectors? Length 1.
4, isn't it?
No, what's V1 not V2? What's the dot product of V1 and V2?
1 over square root of
0.
1.
It's 0.
Oh, 0.
Because I get 1 and I get minus 1. I mean, I get a half minus a half, right? So it's 0. In other words, they're orthogonal, all right? They're perpendicular, which I don't think we talked about in here much yet. But we
We're
will.
going back to geometry.
Right.
All this time thinking.
And so
Or-
what I'm telling you then is that beta is actually a very special basis. It's an example of what's called an orthonormal basis for R2. Now, orthonormal bases are very precious to us because orthonormal bases have the awesome property that the inverse matrix of beta is simply the transpose, which is just fantastic. I'll explain this more another day, okay? But and then of course you can do similarity transformation. You can do beta inverse A beta, which here, with my choice of this symmetric, this orthonormal basis actually is just multiplication by the transpose of the basis matrix A times beta, which is even, you don't even have to calculate the inverse, you just have to transpose it, that's awesome. And I can tell you what's going to happen when you multiply this out. You just get what? 0, 0, 0, and what's the last entry? We proved that this has to happen last time. Beta is an eigenbasis. It's a basis made from eigenvectors. V1 has eigenvalue 0. V2 has eigenvalue 2. There will be a 2 here. And you can check me on this if you don't believe me.
So this happens every single time beta is made from eigenvalues, right?
Except when it doesn't, yeah.
Wait, hold on. So, okay. Getting the orthonormal V1 and V2, like that happens when you're doing eigenvalues, right? Or no? Not all the time.
I mean, how do you construct an eigenbasis? What is an eigenbasis? It's not complicated. Like if I told you you want to find a cat basis, what would it be? It'd be a basis made of cats.
Oh,
Yeah.
feels like a
Right? But thankfully we don't investigate such dark arts. You know? So an eigenbasis is just what it sounds like. It's a basis made of eigenvectors. Values are numbers, I can't even, but I get you. So beta, V1, V2, those are both eigenvectors. This makes it an eigenbasis. And what we proved last time is if you can find an eigenbasis, right, with respect to a given matrix, then there's a similarity transformation by the basis matrix, which takes it to a diagonal form, where the diagonal values are just the eigenvalues corresponding to the basis. Just like that. Now the reason I said whenever it works is the following example. I'll show you another example. So let's suppose A is equal to 3, 0, 2, 3. All right. Sorry, guys.
More coffee, it'll help.
Yeah, it does help actually. Believe it or not.
Do you drink it black?
No.
Wait a
I got
minute.
nothing to prove. I've got nothing to prove. I mean, you buy.
You've got nothing to prove, you're a math professor.
Ah. Oh man. Got me where I live. So P lambda.
With all these funds, I need extra credit. Seriously, I can't do this for free.
Good news. If the matrix is triangular, either upper or lower, the determinant is not 0. The determinant is the product of the diagonals. But more than that, you can see then that the product that whatever's on the diagonal though is then going to be the eigenvalues. Tell you what, Michael, I'll write it this way. Anyway, the point is, if that's equal to 0, you get lambda 1 is equal to 3 twice. In other words, m, you might say m sub 1 is equal to 2. The multiplicity, the algebraic multiplicity of the eigenvalue 3 is 2 here. So then you can look for the eigenvectors. You can look at a minus 3i and see what you get. Well, a minus 3i is what? Oh, there's 2 right there. So I personally can just look at this and go, So that makes E1 equal to the span of, let's see here. What multiplied by this matrix gives you 0? Let's see, the E1 won't work, right? But how about E2? Yeah, it's just E2. I personally can just eyeball it. Now, if you really want me to give you the equation is this. If I look at a minus 3i, I mean, if I look at 0, 0, 2, 0 times uv equal to 0, 0, the only interesting equation here, of course, is the second one, right? So that's the other case. I said that they have to be the same equation. That was not true. But you guys can call me on it.
But I was.
It's okay. Don't worry. I'll make more mistakes.
Well,
There'll be other chances.
Like there's like a reason why I asked certain things. I
Well, it's not that they, but the thing is, they can't be distinct genuine equations, right? The first row here, I would say, is not a genuine equation in some sense, because why? It's the equation 0u plus 0v is equal to 0. Well, that is true, but it's useless, right? It tells you absolutely nothing about u and v. So the first row corresponds to a vacuous equation. The second row corresponds to the equation 2u equals to 0. Now, invariably, you guys get confused with these kinds of problems because you're like, well, okay, so u equals 0. All right, great. And then there's something that drives students to write 0, 0 as an eigenvector on this problem.
But we don't know what v is.
But 0, 0 can't be that.
That's true. Those students are wrong. And I take away all their points.
Wait, hold on. It's like, well, like v can't be 0 in general anyway. We don't know what v is.
Yes, I say v is free. There is no condition on v. V is free. Now, it is free to pick from any value in the garden of values, except for one value. There's one value it may not partake in.
Sure.
0.
It'll be 0, 1.
Is that your little worldview record?
Oh, yes, that was biblical worldview right there. Garden of eigenvectors, yes.
So would the null space of that have would it have
One that I did earlier.
dimension, like would the null space be equal to 1 for that?
Indeed, the dimension of the dimension of the eigenspace here is 1. Okay, so guys, this is why I was a little bit hesitant to agree with Christian just a second ago. He's like, does it always work this way? No, it does not always work that way, because there are plenty of matrices which do not permit an eigenbasis. They do not admit an eigenbasis. This is such a matrix. If I try to find an eigenbasis for it, I simply don't have enough. There's only one eigenvector with eigenvalue 3, and there are no other eigenvalues. You can't write down, there's only one characteristic equation. That's it. It has 3 as its root twice, and that's all you got. So this matrix is not diagonalizable, is what it boils down to. No.
Did you choose v equal to 1 over e1?
Yep. That happens to be consistent with my normalization program I was starting over there. In 1. But, I mean, what I'm trying to tell you is if you use a Texas Instrument calculator or a lot of other things, a lot of times they will normalize to give them length 1, and that's where this mysterious 0.707 blah, 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 blah comes from. So. All right, so that's not the only reason that you can fail to have an eigenbasis. Let me show you another example. Excuse me.
Sure, you're all right. You've been sick for like 2 weeks.
Yeah, it's just 2 weeks.
Not as bad as physics 2.
Gotta get that vitamin C.
Don't worry, I'll be well by fall.
Wait, what's your
That's what you said last semester.
I was better. Hey, I was better at the start of the semester.
Oh, was it allergies? Is that what
I
it is?
think, you know what I think it was? I think it was my cousins. They brought this out of state cold. Well, I'm pretty sure I caught it from, not my cousins, but my children's
They
cousins.
think it's mad pony disease.
Mad pony disease. No, well, I guess the only place you find ponies in my house would be in my little girl's room.
Hey, that's okay. Season premieres on Saturday.
Okay, so I do have some things left to prove, so let me get through this example.
I thought you said you didn't have anything to prove. Or didn't have to prove.
All right, so this is, again, I'll use my minus sign trick because it's nice. So lambda minus 6 times lambda plus 2, distributing the minus, and then plus 1. And so lambda squared minus 6 lambda plus 2 lambda minus 12 plus 20. And let's see here what you got. You got yourself a lambda squared minus 4 lambda plus 8. But you guys are like, hey, this is an opportunity to complete the square. That's right. That's exactly what this is. I'm excited about it too. So this is lambda minus 2 quantity squared plus 4. And once I write that, I can immediately see that this means that lambda is equal to 2 plus or minus 2i. In other words, this is a matrix with no real eigenvalues. So A has no real eigenvalues.
Oh, because they're not real.
That's right. So, of course, you cannot diagonalize it over the reals.
Or can we do it over the
Complexes? Yes, in fact you can. All you do is you,
Am I going to regret asking this?
I mean, you can ask it or not ask it. It's not like I'm going to forget about it just because you asked the question or not. It's something I covered.
Oh, okay.
Just not today. Except that you asked the question, so I guess that's the consequence of your asking.
Yeah. Okay, that's interesting.
So you can find a complex eigenvector U1, complex eigenvector U2, and if you do, if you set beta equal to U1, U2, that's a complex basis, and you do a similarity transformation by that, it will transform the matrix to like a diagonal form with these on the diagonal. We'll talk more about this another day. That's next week, okay? I'm going to stop right there on that. To be more real about this, you can do a similarity transformation on A to find a basis in which it becomes a dilation times a rotation. All right, that's the end of this story. There is a choice of coordinates where A will get morphed into just some constant times a rotation matrix. All right, but more on that later. All right, so some general theoretical issues that we need to deal with here. First of all, I would just, here's some fun facts for you. In other words, fun facts are things that I'm not going to prove today. Fun facts. The determinant of A is minus 1 to the n times the product of the eigenvalues. That's actually still true if you allow for complex eigenvalues. You say, wouldn't it be a complex number? No, they come in conjugate pairs. It multiplies to be real. Like here, if you multiply lambda times lambda conjugate, what do you get? I mean, what happens if you multiply 2 plus 2i times 2 minus 2i? What do you get?
4 minus 4 plus 1, 8.
4 plus 4, 8. What's the determinant of this matrix?
Yeah, 8.
Huh. Coincidence? No. Not a coincidence. The trace of the matrix is equal to the sum of the eigenvalues. These are things I ought to prove for you somewhat carefully some other day. And then here's a mysterious comment for you. If you take the matrix and you plug it in to its characteristic polynomial, all right, this gives you 0. So what I'm saying for this matrix, for example, there's an identity. And he has the proof of it in the 2x2 case in gory detail. And he also has a 3x3 case in the exercises. We proved this later. That's the Cayley-Hamilton theorem. So as it applies to this example, it would say that there's an identity here. A squared minus 4 times A. And you can't add 8 to a matrix, right? So 8 is understood to be plus 8 times the identity matrix. That's 0. That's an identity. This is, what I'm using here is the so-called Cayley-Hamilton theorem. I think Cayley only proved this basically in the cases in your homework, in the 2x2, maybe 3x3 case, and then I think maybe later it was like Frobenius or something who came back. Frobenius wrote this book at the end of the 19th century Frobenius was a beast. And a lot of the linear algebra we have is due to him, in one sense or another, probably. That's a fun thing, though. You can find the inverse for A from this, can't you? Do you see it? Check this out. This is A times A minus 4i is is equal to minus 8i, right? So if you divide by minus 8, you've got a times minus 1/8, a minus 4i is equal to I. So that's the inverse. Yeah. Sorry. Anyway, that's Cayley Hamilton theorem. So now that I've got these fun facts out of my system, let me make a claim for you. Yeah.
Is Cayley a girl? Valid question.
If Cayley was a girl, when people were asked to write papers about women in science, he would be included on the list. There's a professor
Wait.
who regularly says, like, write a paper on a woman in science, not including Emily Noether or the other one.
Alien.
Not Curie. Yeah. If Cayley was a woman, he would be added to that list because he's pretty famous.
Sharon, I think that's two separate last names, not an entire.
Oh! No, that's not Cayley. No, Cayley.
Oh.
Cayley. That is a funny question. Thank you for that.
Any question? You get done on Jeopardy, and then is the
You're on.
I'm gonna stop.
All right, so if x1, x2, x k are eigenvectors with distinct eigenvalues lambda 1, lambda 2, lambda k, then x1, x2, xk is linearly independent set. Now I can prove this in the abstract, or I can prove it in Rn. I'll prove it in Rn just to be friendly. So proof's the same. All right, so and I'm going to give a calculational proof as opposed to an inductive proof. If that's okay with you guys. I have the induction proof in my notes in chapter 11. Okay, so here it is. So what do I want to do? I want to take a linear combination, c1x1, right? c2x2 plus ckxk. And I want to set that equal to 0. I want to show that that must be necessarily the trivial combination, right? So here's the thing. Multiply this by, well, the thing that we've been playing with today was basically this a minus, let's say, lambda, pick a lambda, any lambda, let's call it j, lambda sub j, okay? Multiply that, multiply by that, all right? The equation above. My grammar's awful. Multiply by that. All right, so what we get? We get C1. Properties of matrix multiplication says it's the sum of the products, right? So I mean, that's C1 times AX minus lambda J I times X, right? Plus C2, and I'm going to simplify the second one. What's A times X2? Lambda 2x, right? So minus lambda j x plus plus ck lambda j minus, lambda k minus lambda j times the x's. Sorry guys. If you're lost here, don't be lost. All I'm doing is I'm multiplying each term here by a minus lambda ix. Noticing that we have what? A times x sub I is equal to lambda I times x, right? That's true for I equal to 1, 2, all the way out to k. So that's how I simplify. So like this ax I should really write as what to be like the other terms?
Lambda 0.
Lambda 1. the number external one, times x, right? Now, there's an x everywhere, right? So I can just factor out x, right? So I have C1, oh. That's not an x everywhere. Oh, come on, guys, don't let me get away with that. Like, this isn't the argument I remember. There's a good reason for that.
So it's not like we're supposed
Yeah, it
to
should be x
remember.
line.
One. Oh, you're not like Isaac's. I was like, do you remember in my dream? Blah, 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 blah. Like,
Okay.
I could
No,
do
I
that,
think
then
I-
you'd be creeped out, and you
Nope.
wouldn't want to use me anymore.
I don't remember his dream, actually. But the fourth or fifth time he told me about it, I remember it. But it seems like I have some inside information at that point. So C1 times lambda 1 minus lambda j times x1, right? And then plus C2 lambda 2 minus lambda j times x2. CK lambda k minus lambda j xk equals to 0.
Would it be wrong if you pulled the x1 to the front of that?
No, I mean, you could, I usually write the scalar multiplication to the left, though. I mean, x is a vector. Now, I assumed what about these eigenvalues? They're distinct. What does that mean about these differences? Lambda 1 minus lambda j, lambda 2 minus lambda j?
They're all different?
Yeah, well, in particular, they're all non-zero. You're right, they're all different too. That's also true. They're all non-zero except for one. Voice me.
Which one would be 0?
The jth one would be 0. Oh, bummer. Huh. Yeah, so what does this give us? We just get everything, we still get everything, it's all equal to 0, right? But what? But the jth one is gone, right? So then what would you do?
Add it.
Hmm?
Wasn't that saying that lambda 1 minus lambda j minus lambda j can't be 0, therefore C1, C2, that's not what it's saying?
If we look at the case k equals 2, it works. If we look at k equals 2, we're done already. Right? Because if we were in k equals to 2, k equals to 2, we'd be done, right? Because you'd have C1, I mean, basically there you have C1 x1 plus C2 x2 equal to 0. For example, we could do a minus lambda 1 I x1 C1 plus C2 a minus lambda 1 I x2 equal to 0, right? And so that would have been what? C1 lambda 1x minus lambda 1x, so that goes away, plus C2 lambda 1 lambda 2 minus lambda 2x2 minus lambda 1x2 equals 0. So in the case we just have 2, we're done because this is 0, and we're left with C2 times lambda 2 minus lambda 1 times x2 equal to 0, right? So this being non-zero implies that C2, this being non-zero, x2 is also not 0, right? So that would imply that C2 is equal to 0. And once I know C2 is equal to 0, I can go back to the original equation and then by the essentially same logic, and C1 is equal to 0. That would prove that if you have two eigenvectors with distinct eigenvalues, they're linearly independent, right?
So is that saying that somewhere in there, the lambda sub whatever will equal lambda sub j?
Right, what I'm saying is I can actually rewrite this as a sum of k minus 1 things with the jth one gone. But here's what you can do. You can keep multiplying by other factors. So next, repeat. Multiply by a minus lambda, let's say j2, right, times I. Where j2 is not equal to, where lambda j2 is not equal to lambda j. And then that will remove j2 from the list, right? And then you just repeat this. So if you multiply, basically, what you could, I mean, a more more elegant way to say this is you could just multiply by the product. Let's say j equals to, let's say 2 to k of a minus lambda sub ji. If I multiply by that star, multiply that on star, what I'll be left with is what? What I'm left with is lambda 2 minus, lambda 1 minus lambda 2. Lambda 2 minus, well, I can't, I'm sorry. My brain is not working all of a sudden.
Drink a sip of coffee, you'll get it.
Oh, me. All right, I'll talk about this on the projector next time. I have this written out in gory detail in the notes, but the thing is, it's not just one multiplication. One multiplication works for the 2 by 2 case. I have to do a multiplication by like k minus one of them to get rid of everything except for one term. Then I get the coefficient 0, and then I kind of work my way back up. Yeah.
Would it be possible to do this through induction?
Yeah. That's my second proof. I have a second proof. The other proof usually you see is people prove it by contradiction. They're like, suppose a linear dependence, and then you can imply that the eigenvalues are not that the eigenvalues are equal. That's the other popular argument. So I think I have all 4 in my notes in chapter 11. Each has good arguments in the book. I'm just trying to think my own thoughts at the moment, which is obviously a mistake. Yes, guys.
So probably 145.
Oh, from 145. Sorry. You guys can go if you want this.
But I mean,